The presentation, as Flavia said, is about using data while preserving individual privacy. And here I'm saying individual privacy because actually, coming from CPDP last week, there has been quite a lot of discussion on the value of group privacy and also going beyond individual privacy and so on. So like in this presentation, I'm focusing on individual privacy. Well, I mean, okay, I'm to get back some of the time. I will skip. I will go quite fast on a few things. I mean, we all know that data can be very useful for a lot of use cases, in particular for business, but also policy making, for reproducibility of science, also for competition. I mean, there's quite a lot of talking now about sharing data for competition. So we do want to be able to use data for in a modern society. Of course, the data, as we know, like is often very sensitive, and for example, credit card data can be used to infer income and location about an individual. Search queries data can be used to infer their interests and beliefs, and of course, mobile phone data can reveal a person's location and social network. So typically, traditionally, the idea behind one of the ways, let's say, to use data while preserving privacy has been anonymization, which essentially consists, from an intuitive point of view, in breaking the link between the data and the people to whom the data belongs to, or better, it relates to. And then, once data is anonymized, it can be sent to an analyst for to use it and derive the statistical insights that they are interested in. So anonymization is quite important from a legal point of view because it is essentially outside of the scope of data protection in many cases. So, for example, the GDPR explicitly says that anonymous data is not within the scope of this GDPR, and similar for the Californian Privacy Act. Now, at the same time, the GDPR, and this is something new with respect to the '95 Privacy Directive. The GDPR explicitly says that pseudonymization is not, let's say, an anonymization technique, or better, that pseudonymized data should be considered information on an identifiable natural person, and so pseudonymized data falls under the GDPR. So why is that the case? I'm gonna give an idea now. So first of all, by pseudonymization here, and the term is actually not so well defined, but we take a traditional interpretation of what pseudonymization means. And in this case, if we have a table like this with phone number, sex, date of birth, zip code, and disease, then pseudonymization here would mean hiding these phone numbers, which can be considered direct identifiers. And one option is either we remove them or we transform them into irreversible pseudonyms that look a bit like random strings. So the problem with doing this is that this is not enough to let's say, to prevent re-identification. And now we're gonna see what we mean. So the pseudonymized data set, let's say, can look like this. So here you have the let's say, the randomized IDs. But the GDPR says that this is just pseudonymized data and still personal information. So why? So what happens if I know, for example, that my friend was born on July 8th, 1959, and lives in zip code 89127. Well, at that point, I can see that this is, sorry, I don't know if you can see, I should turn on the pinpointer. I can see that this is the record of my friend. And you might think that that this is not really possible in a larger data set, that maybe this is possible just because we have 5 records here. But actually, In 1997, Latanya Sweeney did precisely this with two pretty big data sets. One was a medical data set, which was available publicly, another a voter list that was available almost publicly. She just had to pay, I think, something like $20 to access it. And the two data sets contain some attributes in common, in particular the zip code, the birth date, and the sex of the individuals. And this was sufficient for Sweeney to find the record of the governor of Massachusetts and essentially re-identify the governor in the medical data set, and find out some medical conditions that he had. So just to simplify the discussion next, essentially here we can call the sex, the date of birth, and the zip code quasi-identifiers. Sorry, this is again the ID, the pseudonymized ID. The blue ones are the blue ones are and the red ones are attributes. The red one is sensitive information, and the blue ones are quasi-identifiers. So quasi-identifiers are the term that is used here to indicate that these attributes might not uniquely identify a person alone, but in combination they might, and in particular that they are the attributes that are assumed to be available to an adversary that tries to identify the person. And the goal of the adversary is to infer the disease, the sensitive information here. So if we look again, and so yes, essentially we can call the auxiliary information the information available, so the set of quasi-identifiers which is available to a hypothetical or practical adversary. So what's happening here is that essentially the attack that Sweeney performed is exploiting the uniqueness of individual records in the dataset. So we have the attacker who knows the auxiliary information, the quasi-identifiers about a person, and matches the unique record in the dataset that has those quasi-identifiers, and so finds out the sensitive information. And Sweeney, when she published the result of this attack, found out that 87% of the US population is unique given only these three attributes. So this kind of attack, let's say the linkage attack, has been proven possible in other practical cases, such as one public data set by the Australian Public Service Commission about, it was essentially a survey on workplace conditions, and another one in 2001 for a public data set about homicides in Chicago, which where researchers were able to identify 35% of the individuals, and actually, this was a pretty sensitive case because the data set included some very, let's say, sensitive information regarding also, who, whether the murder involved drugs, child abuse, and so on. So one of the, let's say, objections that are made against the, let's say, this kind of attacks and their practicability in the real world is that data sets do not contain the whole population, usually. And so, one could say, okay, so if I find your record, if I find a record that looks like yours, how can I be sure that it's really your record? And similarly, like a related question is whether, data controllers can actually protect against re-identification attacks by including just a sample of the population, so not all the population in the data set. So to answer this this criticism, my group essentially looked at this from a let's say formal point of view, and try to understand if we can learn a function essentially that tries to estimate the probability that the record, the unique match in the data set, is actually a correct match in the whole population. So the intuition here, of course, is that, you know, if the record looks very much like you, then it's probably you. Even if the dataset contains only 10% of the population, the probability that someone looks so similar to you is quite low. And this can be formalized and can be estimated. I mean, we could estimate. I mean, the researchers in my group could estimate this function and use it to infer that 99.98% of the people in Massachusetts are unique given 15 demographic attributes. So essentially, this means that in short, like here I'm cutting it a bit short, but a few attributes are enough to make people unique, and the probability that the match is correct can be inferred by an adversary who performs a linkage attack. And if you want, you can also let's say get your own score, uniqueness score on this web page. There is a simple online tool to do this. And actually, I think, yes, there is also a new tool, which I haven't in the slides. I think it's called Observatory of Anonymity. So if you just search on Google for CPG Observatory of Anonymity, you will find the newer version with also more countries. Yes. So the traditional solution to avoid linkage attacks has been record level identification. So the idea here, I mean, the identification is a set of many techniques, but the idea here is that you have the original records, the data set with the original records. You do some de-identification magic, and you obtain the identified version of the records that, you know, in theory should be completely anonymous and should preserve most statistical properties of the data set. Of course, you know, this is, I mean, you can see how this is a very optimistic, let's say, perspective, but this has been the traditional one for quite a long time. And in particular, one very popular de-identification technique is anonymity, which in short requires that every record is indistinguishable from at least k-1 other records with respect to the quasi-identifiers. So this, let's say, caveat is very important here. With respect to the quasi-identifiers, it does not have to be the whole record. And the intuition behind this is that, you know, if this is true, if a table is k-anonymous, then an attack, even if the attacker knows all the quasi-identifiers about the target, then the adversary cannot identify the target uniquely. So here is an example of what this means. Here we have the original table where every record is unique. Yes, every record is unique here. And here we have a pseudo-anonymized version of the table where every record is at least let's say indistinguishable from at least another record with respect to the quasi-identifiers. So you can see here. So actually, in this case, here we have the full record is the same, but here you can see that the other records are indistinguishable only according to the quasi-identifiers. But if you consider also the disease here, they're not anymore. And I will go back to this in a bit on why this is an issue. So to achieve anonymity, there are different techniques, but the main idea is to generalize the data. So, for example, if you have the full zip code, you can turn it into only the first 4 digits, or even just to the second digit. And this is what we did here, right? So here we turn the date of birth into the year birth, and we turn the zip code into the city. Then there are other techniques, but this is not you know, I don't think it's useful to talk about them here. But the important aspect is that all of these techniques modify the data, and as such, they also modify, let's say, the statistical inferences that can be drawn by the k-anonymized data set. So here you have a very simple example where essentially if we decide to anonymize this data set by suppressing this record, then an analyst could conclude that no man can develop Alzheimer, because in this table the only man who had Alzheimer was this one. So we remove it, and it looks like only women can develop Alzheimer. So this can introduce bias in the data. Now, of course, this is a very simple example, but there is an actual privacy utility trade-off for k-anonymity, but actually in all privacy preserving techniques. The problem is that k-anonymity, for k-anonymity, the privacy utility trade-off is typically quite bad, and I mean, k-anonymity has several issues that can be addressed by, let's say, stronger variations of k-anonymity, for example, diversity, closeness, and others. But the fundamental issue is that k-anonymity is based on a notion of quasi-identifier, which essentially does not scale, because if you have more than 10, 15 quasi-identifiers, even to anonymity is very, very hard to achieve while preserving good utility. So, I mean, at this point, first of all, we might wonder, I mean, what exactly, which kind of data sets k-anonymity is used on, because maybe if it's used only on very small data set, then it might actually work quite well. But nowadays, it's very easy to have data sets with more than 10, 15 quasi-identifiers. So how do people apply k-anonymity to these large data sets? And in practice, often the answer is that they cheat, because they select only a few quasi-identifiers, because let's say that there is no mathematical rule to decide what is a quasi-identifier and what is not. So if you have a very large table, but you decide that you have only 3-4 quasi-identifiers, then you can say that you can anonymize the table according to those quasi-identifiers. But the problem is that if just a few more attributes, then your k-anonymity guarantees are completely void. You have absolutely no guarantees of privacy in that case. Okay, so now the identification is still the main set of techniques in anonymization guidelines. So we know that the GDPR is technology neutral. So typically, it doesn't really recommend a specific set of techniques, and the same goes for anonymization. But then the data protection authorities typically release guidelines to give recommendations on how to perform anonymization. And if we look at these guidelines, pretty much all over the world, k-anonymity is really like a core technique, even in modern guidelines. And an interesting question is why that's the case. And the answer is pretty much that k-anonymity gives a very intuitive notion of privacy. It's easy to understand and even to explain. And also it very much fits the traditional to release the data and forget about it. So like that's the model I discussed before. So you have the data, you identify it, it is anonymous, you can do whatever you want with it. And also this is let's say a very practical explanation. So k-anonymity does work for easy examples, right? And typically when you have a page in a document, an A4 page, you don't have enough space to have many attributes. So like in the easy examples that you give, it actually looks like it works. But if you were to take a much larger table, you would realize very, very quickly that the examples do not scale. But instead, there is just an implicit assumption that those very easy examples with 4 or 5 attributes, like the one I gave before, actually generalize to larger data sets, but the problem is that it doesn't. Very quickly, I'm gonna go through the same, let's say, reasoning for big data, because so far we have discussed a tabular, like a table data set, where essentially every record is a row in a table. But for big data, this is not even the case. So by big data, of course, we mean, let's say, high dimensional data, which is automatically collected as a side effect of our interaction with technology. And so, for example, these types of data that I showed before are all types of big data. So in this case, the standard terminology that we used before, so quasi-identifiers, sensitive information, attributes, they don't really work anymore, because typically big data datasets are sets of, let's say, sequences of points. So Bob's record in a location dataset is a sequence of time and location points. And in principle, you don't have quasi-identifiers and sensitive information anymore here, right? So every point in principle can be known to an attacker. Still, we have examples of, let's say, even let's say, companies or public bodies that collect information, I mean, big data sets, and call this information anonymous. This was in London, and similarly in Antwerp, where the city administration decided to track some Wi-Fi signal on the street. And they also claimed that the data was anonymous. So at the same time, there has been quite a lot of research showing that big data sets are quite easy to re-identify. Yes, I mean, this has happened with the search query data, a large data set published by Netflix in 2008, and also DNA data. I'm not gonna talk more about this here, but one experiment that we did was to measure in a data set of 1.5 million people over 5 months how many people were unique according to their movements. So here again, 1 point in the data set means one time and location of the person visited. So for example, the person was in Piccadilly Circus between 10 and 11 a.m. And the question is, how many of these points I need to re-identify someone in the data set? And the answer is that 4 points are enough to re-identify 95% of the population. So this means that if I know 4 points, I can find the unique match in the data set that is your record, and find out all the other locations that you have visited for the past 15 months. And this so this metric, we called it unicity, and it has been used it has been used many times for also for different types of data, like credit card data and apps and so on. Importantly, let's say the techniques that are typically used for the identification and anonymity and so on, they didn't really work on this data set, because in short, let's say generalizing the location and time of the data set worked to reduce the unicity of the data a little bit, but at the same time, it really reduces the utility of the data, and hence of the statistical inferences that you can make using this data. So, like, in short, the trade-off that the privacy utility trade-off that you obtain by generalizing data in location data sets is very bad. So there are different ways to go beyond this the identification model. Here is a paper by my PhD supervisor who discusses some of them. In this talk, I will focus on this square here, which is the question and answer paradigm. So Here, let's say the issues that we have discussed so far with the identification and let's say re-identification attacks was that we took this release and forget model where we essentially give access to individual level data and we have no control over the analysis that the analyst can perform. So a different model is the data query system model, where essentially the idea is that we keep the data set stored on a remote server, on a protected server, and the analyst does not have direct access to the data set, but instead sends queries, so questions about the data set. And the idea is that the analyst can only get aggregate results in return. So example of queries could be, for example, for health data, what is the average age of men with Alzheimer? For survey data, how many employees find their working environment inclusive? And for mobile phone data, how many people were at Pompidou today between 8 a.m. and 12 p.m. And observe that mobile phone data in this case is big data, but as you can see, in principle, there is no real issue here in giving the answer to this counting query, right? There's no obvious privacy breach in doing this. So in principle, it seems that this model can work also for big data. Now, the issue is, okay, this sounds nice, but what if the analyst is malicious? Well, in that case, they can try to actually infer sensitive individual information using queries. And here is a very simple example. So what if the analyst tries to send a query which is how many people named Bob Duffin have salary below 1,500 pounds? Well, in that case, I mean, this query can be either 0 or 1, and this immediately reveals whether Bob Duffin has salary below 1,500. Now we can decide that we do not essentially answer any query that selects less than I don't know 10 users. But the problem is that there are other attacks that circumvent these kind of measures. So, for example, you could have a first query that asks how many people have a salary below 1,500, and how many people not named Bob have a salary below 1,500. And essentially, if you take the difference between of these two queries, it's easy to show that this immediately reveals whether Bob has salary between 1,500 or not, because essentially the result of this query can be either 0 or 1 depending on Bob's salary. So this is called a difference attack, but there are many other attacks in the literature on aggregate data. Typically, one way to prevent this type of attacks is to add random noise to the result of the queries. This intuitively this should prevent this kind of attacks, and so hide private information from the outputs of the queries. So what this means is essentially the researcher or analyst sends the query queue. So the query queue is executed on the database, which is essentially which leads to the true answer queue computed on the original dataset D, and then we add some noise here. So, for example, if the query is how many people at Imperial College are born on 20th of April 1981, then if the true answer is 3, the final output could be 3 plus 1.6, which is 4.6. That's the intuition. Of course, as you can easily understand, the adding this random noise perturbs the result of the query, and so has an effect on utility. And the challenge here is to make sure that the noise is not too much. Otherwise, the utility is destroyed, is heavily affected. But it's also not too little, because then the privacy is not really protected. How do we make sure that we add noise in a proper way? So there are different approaches. One interesting one was the one of Diffix, which is a commercial data query system developed by a startup in Germany, Erclock, and a Max Planck Institute. And in short, it gives access to SQL syntax and gives answer that in theory should be privacy preserving. And the goal is to provide good utility for pretty much every application, and even allow infinitely many queries from the analyst. In particular, the company behind Diffix claimed that Diffix provides GDPR level anonymity for all use cases. I will not discuss exactly how Diffix works here because it's quite technical. But I mean, I would just say that even given just infinitely many queries is something quite impressive, because typically, from the literature on attacks against data query systems, we know that this is a very challenging thing to do. So in short, in 2018, we found a vulnerability in Diffix's system, and we were able to perform a attribute inference attack, where essentially knowing only six attributes, which are essentially the quasi identifiers that we discussed before, we could infer some of the victim's sensitive attributes with very high accuracy, above 90%, and importantly, using only 32 queries, which is 32 queries are very few for an attack of this effectiveness and, let's say, this coverage. So Erclock acknowledged this attack and assigned severity very high, and you can read more about this on our blog or on the paper which we published in Usenix. A different solution to add noise is differential privacy, and probably many of you have already heard about this. So in particular, differential privacy became quite popular. Quite known to the public when Apple implemented it in iOS and macOS devices in 2016. And in really very briefly, differential privacy is a definition of what it means to preserve privacy for an algorithm. And the intuitive idea is that, if a record is in the data set or not, essentially nothing will change in the result, which is given by the differentially private algorithm. So in practice here, if you have the analyst that sends the query on a database and obtains a certain result, if this database has one more record and the analyst sent the same query to this new database, then the two results here should be pretty much similar. Technically, actually, it's the distributions that should be similar, but this is a technical point. So again, here, of course, we have to decide how much noise to add, and this is quantified by a parameter epsilon, which is called privacy loss. And this is again very technical, but the idea is that small epsilon means noise, which means more privacy but less utility, and vice versa. Large epsilon means less noise, less privacy, and more utility. So differential privacy is great in theory, but very hard in practice. And on the upside, it has great properties because it gives mathematical formal guarantees of privacy. These guarantees hold against any adversary, regardless of the auxiliary information that might be available, which also means that it is future-proof because it is robust against any auxiliary information that might be available, even in 50 years from now. And there is a lot of research that has been done on differential privacy. There are more than about 5,000 papers with differential privacy in their title. But the problem is that differential privacy is quite impractical in most settings. It is hard for controllers to implement it and for data analysts to use it. The total theoretical privacy loss grows quite quickly, to the point that essentially the mathematical guarantees of privacy that you have are not meaningful anymore. And also, on the utility side, differential privacy can hide important insights on smaller groups, and this is a very hard thing to prevent when you want to do privacy, because smaller groups are by design hard to protect when you want to protect privacy. But yeah, differential privacy is particularly hard to, let's say, avoid this kind of issues. So it looks like we're in trouble because the identification doesn't work. Data query systems seem good, but can contain serious vulnerability, and differential privacy would solve the problem in theory, but it is not really practical so far, at least yet, as a standalone technique for general purpose analytics. So what do we do? And so here is a possible, let's say, approach to find a practical solution for the short medium term. So I don't have much time left, so I will go quite fast on this. So here the idea is that so far, even when we change let's say the model to data query systems, we have considered a silver bullet approach to anonymization, which means that we were looking for a fully technical solution that is expected to automatically protect privacy against any adversary and automatically give good utility for most use cases. And this approach, this silver bullet approach to anonymization, is really a legacy of the traditional de-identification release and forget model. And of course, this would be ideal, but in practice it doesn't really seem to work. And so the question now is this really necessary to get good anonymization? And if we look at the GDPR in recital 26, the GDPR explicitly says that to understand whether data is identifiable, we should take into account all the means reasonably likely to be used. So not all hypothetical, theoretical means, but only those that are reasonably likely to be used. And in particular, this means taking into account all objective factors, such as the cost and the amount of time required for identification, taking into account the available technology and future technological developments. So this, in particular, is translated by guidelines into some contextual factors that should be taken into account, and in part the Article 29 Working Party, which is the predecessor of the EDPB, in their guidelines on anonymization from 2014, explicitly include control mechanisms, the availability of public information resources, and let's say the setting where the data is disclosed, the auxiliary information. These are all elements that the Article 29 Working Party include in the let's say the factors that should be considered to determine whether data is anonymous or not. So this brings us to an alternative to the silver bullet approach, which is to actually try to minimize the attack surface and to increase the costs and the risks that executing the attack can have. And these are just security principles, right? This is nothing new, that we know this, but this has not really been applied so far much to the case of anonymization. Of course, these principles are, let's say, possible to implement for controlled settings, but for open data, it's very hard. But at least for controlled settings, this is something that we can hope to achieve. How do we do this? So here is again let's say a set of principles which are really borrowed from the field of security, and in particular from the concept of defense in depth. And the idea is to combine choices and technical measures with organizational measures to ensure that we, as we said, minimize the attack surface and increase the cost of the executing attacks. I don't have much time left to discuss this, but here the main idea is to have measures like authentication, login, query rate limitation for all the queries that are sent by the analyst, but also to make sure that the system enforces aggregation for each query. So we implemented this principle in a data query system, which is called Opal, which is an open source privacy preserving platform for location data, and it's developed with different partners. And in short, Opal uses the MapReduce paradigm to enforce aggregation. So the idea is that every algorithm that runs on Opal has a map component, which is the algorithm, the code that is executed on each individual record. And then there is a choice of a reduce method to aggregate the results that come from the map function. And the reduce method is just like a count or sum or median. So an example here is, to count the total calls made in Paris today between 8 and 12, you can count how many calls the first user made, how many user the second user made, and so on. And then the reduce method sums the individual level values. Yes, and they say that this model makes it easier to audit the algorithm for let's say for potential privacy attacks. Each algorithm in Opal can include a privacy module to include additional measures to protect privacy, like noise addition and so on. And we implemented this on a density algorithm.
Andrea, I would ask you to
Yes, these are the last two slides. Yes,
so that we have at least a few minutes for Q&A.
Yeah. So of course, this model is very far from perfect. And in particular, there are in theory privacy attacks can still be possible. You could have colluding adversaries. You could have unknown attacks that you cannot really detect. And also for utilities, not really flexible. And designing algorithms can take time and expertise. So this is really not a perfect solution, but it is something that can be practical in the short to medium term. So where do we go from here? There are different, I think, avenues to work on. In particular, probably more research on attacks to understand really what are the attacks that are possible in practice. Also, privacy threat modeling, which is something which is not really applied often in this case. To formalize the privacy guarantees of techniques other than differential privacy. And also something very useful in practice would be to develop attack libraries that assist controllers for anonymization, because it's not that we cannot expect any controller to go back to the academic papers to understand whether the data they want to release is safe or not. We really need to streamline these tests. Yes, and thank you for attention. And yes, if you have questions, I'm happy to answer.